problem 5, in my estimation, is relatively straightforward. There are actually a lot of ways that you can make this molecule. You can go a lot of different pathways. So the key steps in this synthesis are that you have to somehow make this. So you have to somehow introduce this group. So if you look at this, and if we look at what our standard disconnections are, we know how to make a carboxylic acid on an aromatic system, and we use a Grignard reagent there. We look at the amine. So all we've done is we've alkylated the amine. So you can pretty easily draw a disconnection there. You can also pretty easily draw a disconnection there. And then the final disconnection that you need to make is there. And actually within this problem set we've seen a lot of the examples of this chemistry. So, and we want to start with aniline, which is this aromatic amine here. So the approach that I chose to put on the alkyl substituents on the aniline is I chose to show reductive amination, just so that it would refresh everybody's memory. But you could just as easily substituted something like this, just the aliphatic bromide, or iodide, or any halide. But when you use this aldehyde, what you form is this imine, and then hopefully you recall that this particular reagent, this is basically the same thing as sodium borohydride, but it has very, very selective reactivity for these imine species. So this whole process is called reductive amination. If you're not familiar with it, just look it up in your book. They have very nice examples of reductive amination. And so this is, again, a second reductive amination. So we will take this secondary amine, form the imine with formaldehyde, and again react it with sodium cyanoborohydride. This at this point is still an ortho para director, so it'll either direct at this position, the ortho position, or this position. This is also another reason why I chose to do it in this direction. If you wanted to, you could have, as your first step, brominate at this position. One of the reasons that I chose to go this way is that once you have your alkyl substituents on your aniline nitrogen, that will increase the steric requirement at these two ortho positions. So when you brominate, and here I'm just adding iron tribromide, facilitates the reaction. We went over that both in the lecture and it's covered in the book, but you could just as easily use Br2 and AlCl3. So again, this is just another Lewis acid. So standard electrophilic aromatic substitution, you then take this bromide and then you form with magnesium metal the Grignard reagent, right? And then, which is the equivalent of that, a strong nucleophile at that position. Then you add CO2, right? And then so this would be a carboxylic, this is going to become a carboxylic acid. I'm not going to draw the rest of the molecule. That's after this step right here. And then thionyl chloride will take this carboxylic acid and convert it to the acid chloride. And then that is a very good electrophile. And then you treat it with this nucleophile, this position. And again, remember, why is the amine not reacting? Why is the hydroxyl reacting? This is a tertiary amine, right? If it was a secondary amine, the amine would be more reactive. If it was a primary amine, the amine would be more active. But here we have a tertiary amine versus a primary hydroxyl. And then, so you get the product.